Welcome to The Explainer. So, you've probably played around with something like ChatGPT, right? And maybe you've had that moment of, whoa, how does it do that? Well, you're in the right place. Today, we're pulling back the curtain and getting into the real nuts and bolts of how these large language models actually work. I mean, we've all been there. You see what this stuff can do, and it's amazing. Maybe even a little bit spooky. It really does feel like magic. But is it? What's really going on behind that blinking cursor? Well, let's get into it. Turns out, it's not so much magic as it is some seriously clever math. Okay, so to really pull apart this magic trick, we got to start at square one. Like, what do we even mean when we throw around the term artificial intelligence? Well, at its most basic level, AI is just about making something that acts in a way a person would call intelligent. And here's the thing. If you can explain it, it's not magic anymore, right? And trust me, even though AI seems incredibly complex, it can be explained. So how do we get a machine to act smart? You could try to write millions of rules by hand, like if this, then that, but that's just impossible. Instead, we use something called machine learning. It's kind of like teaching a kid by showing them a ton of examples instead of just a rule book. We feed the machine a mind-boggling amount of data, like picture all of Wikipedia and then some, and we tell it, go find the patterns. What comes out of that is what we call a model. It's basically the machine's own simplified map of how something super complex, like our language, works. Okay, but finding patterns. What does that even mean inside a computer? How does a machine learn? To get our heads around this, let's use a really cool metaphor. Think of it like a simple electrical circuit. Okay, let's pretend for a minute we're building a really simple self-driving car. All we want to do is connect the car's eyes, its sensors that see what's around it, to its hands and feet. You know, the steering wheel, the gas, the brakes. Now, if we just wired every sensor to every control, you'd get total chaos, right? The car would try to brake, accelerate, and turn left all at the same time. Not good. So what we do is we put little control knobs, you can think of them as volume dials or resistors, on every single wire. And then we train it. We show the car tons of examples of a real person driving, and we just keep tweaking those little knobs over and over until the car's actions perfectly match what the human would do. That constant tweaking, that adjustment, that's the learning. Okay, so you've got this idea of a circuit that learns by tweaking knobs. Now, here's the leap. Here's where it gets really mind-bending. We can take that exact same concept and apply it to something way more complicated than driving a car. We can apply it to language. So instead of the circuit's goal being drive the car, its goal becomes something surprisingly simple. Its entire job is to guess the next word. That's it. That's the whole game. When you strip everything else away, a large language model is just a giant, superpowered, predictive text machine. But, and this is a huge but, the scale is just astronomical. I mean, think about it. If you have a vocabulary of, say, 50,000 words, a circuit that just looks at the last 3 words to guess the next one would need, wait for it, 7.5 billion connections. 7.5 billion little wires with knobs on them. That's just not going to work. It's way too big. Yeah, that level of complexity is a total non-starter. So some really smart people came up with an ingenious solution, a clever trick to make the problem manageable. They basically broke that one giant, messy circuit into 2 smaller, much smarter pieces. The first piece is called the encoder. The best way to think about it is like a zip file for words. It takes a word from our massive 50,000 word vocabulary and just squishes its meaning down into a tidy little package of a few hundred numbers. And what's cool is that words that mean similar things, like king and queen or happy and joyful, end up with really similar numerical code. And then you have the second piece, the decoder. And you guessed it, it does the exact opposite. It takes that little compressed numerical package and unzips it. It expands it back out and uses it to make a really good guess about which of our 50,000 words is the most likely one to pop up next. This whole encoder-decoder setup is just way more efficient. Okay, so that encoder-decoder idea was a huge step. But the real breakthrough, the thing that totally unlocked the insane power of modern AI, that brings us to something called the transformer. So what is a transformer? Well, you can think of it as that same encoder-decoder system we were just talking about, but with an absolute game-changing superpower baked right in. And that superpower is called self-attention. So how does self-attention work? Let's look at a simple sentence. The alien landed on Earth because it needed to hide. Now, for us, that's easy, but for a machine to understand that sentence properly, it has to figure out a really important connection. What does the word it refer to? You see where this is going? That's exactly what self-attention does. It gives the model the ability to look back over the entire sentence and draw lines between words. It lets the model see, clear as day, that the word it points right back to the alien. And it's not just one connection. It's doing this constantly for thousands of relationships all at once within a single chunk of text. This is how it builds up a really rich, deep understanding of context. That ability to see how all the words relate to each other, that's the secret sauce of the transformer. It's the reason these models can write stuff that sounds so incredibly human. So let's put it all together. What we have is this super powerful word guesser built on this transformer idea, and it's been trained on a truly staggering amount of text from the internet. And that fact that it learned from the internet explains both why it's so amazing and also why it has some pretty serious flaws. So why do these things seem so smart? It's because they are the ultimate pattern matchers. They have seen billions, literally billions of examples of everything humans have ever written down. Poems, computer code, casual conversations, homework assignments, you name it. So when you give it a prompt, it's not thinking. It's generating what a statistically average response would look like based on everything it's ever read. But, and this is really important to understand, there's a huge catch. Remember, it's a word guesser, not a truth finder. It has zero concept of what is true or false, right or wrong, which means it can, and often does, just hallucinate. That's the technical term for it, just making stuff up with complete confidence. And since it learned from the internet, it's going to soak up and spit back out all the biases and misinformation that's out there. And one last thing, since each word it guesses becomes the input for the next word it guesses, one little mistake can cause a whole chain reaction of errors. So what's the big takeaway here? It's simple, but it's absolutely crucial. You have to verify what these models tell you, always, especially if you're using it for something important. The rule of thumb should be, if you're asking it to do something that you can't check yourself, you really have to stop and think about whether you're okay with acting on a mistake. So in the end, we come full circle. It's not magic, is it? It's an unbelievably complex, but ultimately understandable system of circuits, statistics, and incredibly sophisticated pattern matching. And that leaves us with one last question to chew on. When we're chatting with these amazing tools, are we talking to a genius? Or are we just talking to the world's best mimic?